Welcome everyone to another lesson on Khadija Academy. Before we start this lesson, hit the subscribe button, the notification bell, and the like button for the YouTube algorithm. Now let's go and start our lesson. Hey everyone, in today's lesson we will understand how can we use the vector control, in which we are going to use the DQ or the direct axis and quadrature axis currents in order to control our DG. Now how can we combine what we learned? Now what we are going to use is called the voltage orientation. Vector control, voltage orientation. You have to know that vector control has many types under it. There is a field oriented control, there is indirect field oriented, direct field oriented, many types. Okay, one of these is called the voltage orientation control. Now what I'm going to do here, if you remember from the previous lessons, that we take the vector voltage, the final vector which representing the three phase, the resultant rotating space vector, and we divided it into two components, one in the direct axis and one in the quadrature axis, right? Now if you remember correctly that our VBCC here, or this is a resultant vector of the three phase grid voltage. Okay, the resultant vector, this is a VA, VB, VC, the three phase of the grid, and this is the resultant vector, okay, which rotates in space. If you remember, it was rotating like this in the space with an angular velocity equal to the synchronous speed, right? Omega s. It was rotating with omega s, and then we draw it to the rotating frame DQ, which was rotating also with omega s. Okay, so what is exactly that the angle that VBCC makes with phase A? So you will find that if we draw this vector, the resultant vector, like this, V, which is the resultant vector, you will find that the angle that is formed with phase A, or with beta, since they are on each other or oriented above each other, you will find that theta here is equal to omega s multiplied by t. So this one, its orientation, it changes with time, right? It keeps rotating all the time, and its position theta is defined by omega st. So what are we going to do? In this example, we are going to do voltage orientation, in which what you are going to do, remember that in order to get DQ frame, we need transformation angle, theta, right? The transformation angle. And we said that in the previous example, which we have done, we selected theta as omega st. This is exactly what we are going to do in this example. If I selected the transformation angle of the DQ frame equal to the angle of V, what will happen is that we will have the frame like this. D will be oriented above, the axis will be oriented above the voltage, and 90 degrees from it, the Q axis, like this. So what you will find that between them 90 degrees. So you'll find that D axis is oriented with V. So if we draw it in space at any given time, like this, let's say our V is here, okay, then D will be like this and Q will be like this. They will be rotating with our voltage vector. So in this case, the D axis is always oriented in V. Why? Because we selected the angle of the transformation equal to the angle of the voltage vector. So as if D is always in phase or oriented above voltage vector. Okay, that is what we call voltage orientation. So if we draw it, it will be like this. So as if we have D axis and Q axis with an angle theta, and they are oriented above VBCC. And you will find that we will have ID in the direction of D axis, as you can see, ID vector, and IQ is in the same direction of Q axis, and their summation gives us the current of the DG at any given instant, right? IDG. Okay, so what we did is that when we put the D axis on VBCC, it means that VD will be like this and VQ will be like this, right? Since I and the IQ here and the ID here, right? So what you will see is that VD is oriented on VBCC and VQ is oriented on Q axis. And as you can see that there is no component of VBCC on VQ, right? So VQ in this case will be equal to 0, right? Because D axis is all in direction of VBCC. So what we will see is that VQ is equal to 0, then it means that VBCC will be exactly equal to VD. Okay, because as you can see here, all of the voltage is on D axis. There is no component of VBCC on Q axis. So VBCC will be equal to VD. However, there is a small trick here. When we use the transformation, as you will see, we used the power invariant transformation. Okay, which makes power before ABC is equal to power at DQ without any modifications. So you'll find that the voltage VD is not equal to VBCC here, which is Vmax, okay? Vmax in this case, it does not equal to VBCC. There is something here which we need to be added. This factor is root 3 over 2, VBCC. Now, where did we get root 3 over 2? Let me get back here. If we get back to the previous example here, this point, if you remember, when we used the, let's get back to in example 1, okay, here you can see that in this transformation, 3-phase IA, IB, IC, which is similar as VA, VB, VC, okay, and we used the power invariant transformation, which keeps power constant. We found that there is I alpha is equal root 3 over 2, I max, and I beta root 3 over 2. Similarly, for IQ is equal to 0 and ID root 3 over 2. So what we can see here is that ID compared to maximum value of the 3-phase multiplied by root 3 over 2. So this is the same factor that I used here in this example or in this explanation. You can see that VD root 3 over 2. Why? Because we used the power invariant transformation. And I will explain why did we use the power invariant transformation right now. So what we can see that conventionally the D-axis is aligned with the voltage vector of the BCC, the resultant vector. Now what we will find that VD is equal to root 3 over 2 VBCC. And similar as ID, in the example, ID was equal to root 3 over 2 I max. Here VD will be equal to root 3 over 2 V max. So the VBCC which I'm talking about here is the maximum value, okay, or peak phase value. That's why you'll find that VBCC is the peak phase value at the point of common coupling. Now from this we can get the power equation, which is VDID plus VQIQ, which we proved in the previous example by making VQ, here we are talking about VQ equal to 0, then it will be VDID equal to VD, which is root 3 over 2 VBCC, and ID as it is. For the second equation, for Q, we know that VQ is equal to 0 because the D-axis is oriented on the voltage, okay, oriented on the voltage itself. Okay, so it will be root 3 over 2 VBCC IQ. Okay, now what you will see here, what you can notice here in these two equations is that you can see root 3 over 2 V max, right? V max, which is the maximum voltage of the phase of the three-phase system. Root 3 over 2 V max, this value here is a constant, right? Constant value, doesn't it change? This one is also a constant value. So what we can learn from this is that by controlling ID, I can actually control active power injected. And by controlling IQ, I can control reactive power, right? So this is how what we did is that by using the direct access current, we can control active power. And by controlling IQ, we can control reactive power. This is called decoupling. And instead of controlling both of them at the same time, we are now making them decoupled. Each one is separate from each other, in which the current component of the DG, ID of the DG, can control active power. And the quadrature axis current IQ can control reactive power. How did we achieve this? By voltage orientation. When we make the voltage, the D-axis is on VBCC. Now someone will say, hey, but isn't this VQ equal to 0 means that IQ equal to 0? No, it doesn't mean this. Why? Because if you remember that the two currents, the currents at the grid side, they have a phase shift between them. So for example, if VBCC was like this, the current itself can be lagging, right? Lagging by a certain angle. I at BCC. So it means that ID and IQ are not necessarily equal to, or IQ is not necessarily equal to 0, because IBCC is not in phase with VBCC in this case. Okay, so what you will see here is that here D-axis oriented on VBCC means that all of the voltage is in D-axis direction, which making VQ equal to 0. This led us to this decoupling effect, controlling of ID and IQ. Okay, now you will find that this is not only the way to control it. Other papers or other research paper, say that I'm going to select the angle theta, which is the transformation angle, as omega st, which is the angle of VBCC, minus 90 degrees. And I have used this in one of my own papers, in which you will find that if you do this, if you used a transformation angle like this, let's draw it. So if we have VBCC like this, okay, then what you will find is that this is the original D and axis and the Q axis, and this is the angle theta, right? Take theta, which is omega st, and subtract from it 90 degrees. So it will be shifted by 90 degrees, so it will be like this. Okay, so as if we take d-axis from here and subtracted 90 degrees. So d-axis, instead of being here, it will be like this, d-axis. So the d-axis like this. And since it's rotated by 90 degrees, q-axis will also be rotated by 90 degrees and take its place. So the q-axis will be here. So in this case, in Clark-Park transformation, we used an angle of theta equal to omega st minus 90 degrees. In this case, we used transformation angle equal to omega st. Okay, so in this case, VBCC is on d-axis. However, here you'll find that q-axis is on VBCC. So you'll find that VD is equal to 0 and VQ will be equal to root 3 over 2 VBCC. Okay, that is exactly the difference between these two. So by controlling theta, we can do a lot of things. The transformation angle of the Park transformation or Clark Park transformation. By controlling it, we can control where are we going to orient these axes, which can help us to achieve different control. So in this case, we controlled power using ID and Q using IQ. If you do the reverse, if you switch this by 90 degrees, then you'll find the reverse will happen. ID VD will be equal to 0 and 0. So we'll see that power is controlled by IQ and Q is controlled by ID. You can see the relation is now reversed. Okay, so there are many control strategies that you'll find in research papers. Now let's continue what we did. So what we see now is that power, ID, Q, IQ. Thank you for watching this lesson. I would like to invite you to our academy, Khadija Academy Premium membership, which will help you learn more about electrical engineering. In this academy or in the academy membership, you will find that we'll have more than 100 courses in math, electrical engineering basics, power engineering career preparations. For example, we have electrical design, we have courses on electric circuits, power electronics, ETAB, MATLAB, solar energy, wave energy, wind energy, and much more. You can join our membership for just a small fee per month, or you can just have a lifetime access in which you will get all of current courses and classes, and you can have them forever. And not only this, but any new courses that will be created, you will be able to watch it for completely free. So what are the classes that I will learn in this membership? You will find different classes in electric circuits. You will find in transformers, magnetic circuits, machines, power electronics, load estimation, lighting design, lightning also design, earthing system, cables, generators, light current systems or low current systems, off-grid design, on-grid design. Very lots of classes and courses in different topics.